Greetings and welcome to Physical Science at Hack. A purpose of this video, and many others that we will have like it, is to go through some sample problems for what we'll do for each chapter. Now, for the introduction isn't specifically a chapter in our textbook in our physical science course, but I'm going to go through a basic introduction to really significant figures. And we can go through and look at those and try to understand what we need to use to really be able to understand, how many numbers are significant when you're doing a calculation. When you put a problem into your calculator, it'll usually spit back a very large number, whole ton of decimal points. And what we find out is that most of those are meaningless because there's a limit to how accurate our observations can be. When we measure something, there is inherently some error in it. Try to measure something, take a ruler and try to measure something. Is it precisely 2.5 centimeters? Or could it be 2.6? Or could it be 2.55? Or could it be 2.51? It is not 2.5 precisely. There's going to be some variance in it. And that leads to errors and limits the number of figures that are actually significant in the answer to a problem. And we'll see this many, many times as we work through this course. So let's get started here. The first part of this I'm going to bring up, we're actually going to look at a few numbers here. I'll bring up a table of numbers we can look at. And what we want to look at is how many significant figures there are in each of these numbers. So I'll be able to talk about some of the rules that we have for significant figures and how many there are. So one of the rules for significant figures is that if a number is not zero, it is significant. So if it is a non-zero number, it is a significant figure. So when we look at a number like 25, 25 has two numbers in it. Neither one of them is zero. So both of those numbers are significant, and that would mean this would have two significant figures. Now, let's look at some other numbers. What if we look at something like a number in scientific notation? This is 1.0025 times 10 to the third. How many significant figures does it have? Well, for the purpose of counting significant figures, you don't have to worry about the exponent. This times 10 to the third power. That is not meaningful when we look at the number of significant figures. All that you have to look at for a number in scientific notation is those numbers that are to the left of the power of 10. So in this case, there's 5 of them. Now, 2 of them are zeros, so we have to consider my first rule that I gave you said that non-zeros were significant. Well, zeros are significant if they're in between other significant figures. So these 2 zeros are between non-zero numbers. You have a 1 here, and you have a 2 and a 5 here. And that means that these zeros in between the 2 significant figures are also significant and gives us a total of 5 significant figures in this case. So this would have 5 significant figures because those 2 zeros are significant. Why are they significant? Because they are in between other significant figures. Now let's move on to our third one. Third one is a decimal, 0.2501. It has 5 figures in it, 2 of them are zeros. By our reasoning in the previous one, we know that this 0 must be significant because it's between 2 other non-zero numbers. However, this first 0 is not significant. Why is it not significant? Because you do not count any zeros until you reach a non-zero number. So when you start from the left, you have to work your way until you get the first significant figure before you begin counting any. So any zeros leading the numbers out here are never significant. And in that case, you'll just have the 3 numbers, the 2, the 5, and the 1, which are significant, plus the 0 that is in between the 2 would be significant, and that would give you a total of 4 significant figures in this case. Now, let's look at our next one. The next one is 1.5 times 10 to the 15th. That is, again, another number in scientific notation. And as with the previous one, these numbers don't matter. There's only 2 digits to the left of the power of 10, That means those two, both not being 0, are both significant and gives us 2 significant figures. Now another decimal in the 5th problem that we're looking at, we have 0.0098. 5 digits in the number, but 3 of them are zeros. They're all leading zeros, so they do not count in the significant figures. This is just only the 9 and the 8 will count. Because those zeros come before any other number, they do not count as significant figures, and leaves this also with only 2 significant figures. Now, as we look down a little bit more here, let's scroll down a little bit and look at our last 5. We have 3 more. We have first is 400. Now that's 400, but note that there is a decimal point here. That decimal point makes the difference. When you put the decimal point there, you are saying that those zeros are significant. So in this case, you have a 4, and you have 2 zeros. The 4 means we can start counting these zeros. But if there were no decimal point here, we would be saying we don't know whether that's 400, or maybe 398, or 415. So when we put the decimal point, we are saying that those 2 zeros are significant. So when you see a decimal point like that, after a non-zero number and maybe some zeros, that makes those zeros significant and means that 400 with a decimal point has 3 significant figures. Now, next one, 3.14159. You may recognize that as the first few digits of pi. Again, there are no non-zero numbers there. Everything is non-zero, and that means that every single one of them counts as a significant figure, and that would give you 6 significant figures here. The next one also has 6 figures, but 2 of them are zeros. Again, those 2 zeros are embedded in between other significant figures. There's no leading zeros, and that means that this one, likewise, has 6 significant figures. Now we have 400 again. We did 400 before. This 400, you'll note, does not have a decimal point after. Because it does not have a decimal point, those 2 zeros are not significant. We're just saying it's 400. It could be 400, but if you're measuring something, we're just saying that we cannot say, for example, that could be anywhere between 351 and 449. We don't know what those other 2 digits are. When we put the decimal point there, as we did a couple steps ago, that made those 2 zeros significant because we were saying that, yes, we know this a little bit better. So putting that decimal point in makes a big difference in how many significant figures. And in this case, there's only going to be 1. Only that 4 is significant. Now our last one here has a whole bunch of zeros. It's got 6 digits in it. There are no leading zeros, so that means that there are no leading zeros to eliminate. But there are 4 zeros all in between the 2 2's. The 2 2's make all of those significant, and once again, like a couple ago, we have 6 significant figures here, so all of those are then significant. Now this becomes very important in this class because we will do a number of calculations, and when you give an answer, you don't want to give the answer in more significant figures than are warranted by the problem. So let's look at a number of calculations. We're going to do 6 of these to look at some calculations involving significant figures. So let's look at these first. We're going to look at each of these problems here and do the calculations, but in the end we want to express our answer in the correct number of significant figures. So you don't want to give just the answer that comes out of your calculator. It'll have significantly more figures, and most of those are meaningless. So let's do the first one as an example. If we multiply, if we just put these in our calculator and multiply, we end up with what? Well, we will get an answer of 36,882,266, and so on. So that will keep going. Now, that number is in the wrong number of significant figures. We're referring it to much more precisely than we really know. How many significant figures should it have? Well, it depends on two things. It depends on what kind of math you were doing. In this case, we're multiplying. If you're multiplying or dividing, your answer can have no more significant figures than the least of the significant figures in your numbers going into that. So let's look at an example here. If we look at these, 2.000, the decimal point, when you put zeros to the right of the decimal point, they become significant. All those zeros are significant as long as there was a non-zero number before them. So this one has 4 significant figures. Pi, 3.14159, we did that not that long ago. That has 6 significant figures. And 5,870, note there's no decimal point, that has 3 significant figures. So of these, we have 4, we have 6, and we have 3. We then go with the lowest one, 3 significant figures, and that's all you want in your answer. And that means the answer for this would be 36,900. And that would be the answer to the problem. It would have 3 significant figures. Note there's no decimal point after those zeros. And that means that we do not know what those were. It was rounded off. This is our approximation based on the numbers we have, but that only works if all of those numbers are exact. If any of those are a little bit different, as you know, pi has more digits. You could have put more numbers on there. So that is as significant as we can give this number. Let's look at the second one here. Second one also is multiplication, so we have to do the same thing. We have to look at the number of significant figures in each of the numbers going into it. A leading zero, recall, does not count, so there's only 2 significant figures here. This one has no zeros, so this is going to have 6 significant figures. And the last number in scientific notation has 3. 1, 2, 3 there, so that would have 3 significant figures. So we're going to multiply this in our calculator and find out that there are going to only allowed to have 2 significant figures in the answer. So this is a big one to do. This one does have scientific notation. When you put things in scientific notation, you do not want to use the multiplication key. I get a lot of students who want to do this as 2.14 and then multiply it by 10 to the second power. That does not work in many cases because then your calculator sees it as 2 separate numbers. It sees it as a 2.41 and it sees it as 10 to the second or 100. That can cause problems, especially when you're dividing. So it is recommended there should be, and usually is, an EXP key or a double E key, depending on your calculator, or something similar. If you're not sure, let me know your calculator type, and I'll be happy to look it up and find out what you have to enter those numbers in scientific notation. But you will need that for this course because a number of our calculations will involve numbers written in scientific notation. So let's do this. If you put all these numbers into your calculator, multiply them all together, you're going to get, in this case, 27,483,047.6756. Again, most of these numbers are insignificant. They are meaningless simply because we don't know the numbers that accurately. The first one is only 0.25. Is it really exactly 0.25? Is it 0.25 and zeros going on forever? Or is it 0.253, which would change this number significantly? When we write the number as 0.25, we're saying that's as far as we know it. So we have to write this answer then in 2 significant figures, which means we only keep the first 2, and that would be 27 million. So our insignificant figures, our answer would be 27 million, or we could rewrite that in scientific notation as 2.7 times 10 to the 7th power. Either of those would be correct. In most cases, when you've got that many zeros, you'll find it much easier to write things in scientific notation. So Either of those would be correct. They're both two significant figures, which is the least of the ones that we have in our number going into it. Now those were multiplication. Let's look at some division problems and see what we get here. Our first one is 1.89, or 189.28 divided by 3.85. Let's scroll that up here a little bit. And let's see what we need to do here. Again, we put those numbers in our calculator to do the calculation. But first, let's look. How many significant figures do we have up here? Well, in this case, we have 5 significant figures. And in this case, we have 3. So our answer is going to only be able to have 3 significant figures, because that's the least of the ones going into it. However, if we divide this, we find out that it is equal to 49.16366, and so on. 6 3's going on forever, a repeating decimal. Again, most of those are not significant. We only want the first 3, and that is going to equal 49.2. That will be our answer in the correct number of significant figures. Now let's look at another one with division. This one is division with scientific notation. Again, let's count first of all how many significant figures are in each. Here we have 2. Here we have 3. Our answer can only have 2 significant figures. When we divide these two numbers, we should get 21.028. Now, if you divide those and you do not get 21.028, it's likely that you are using the multiplication key to enter the exponents here. That's what I warned you about up in number 2. Honestly, in number 2, it would have made less of a difference if you did things right. Here, it'll make a big difference. It will look at this, if you put this in with multiplication, as taking 4.5 times 10 to the 6th, 4.5 million, dividing it by 2, and then multiplying the whole thing by 100,000. That's because it's doing the correct order of operations when you enter those as different numbers. If you use your exponentiation key or your double E key, that will work it out correct, but you will be getting 2.1 or 21.028 for your answer. Now, we only want it in 2 significant figures, meaning our answer would be 21. So, condense that down to 2 significant figures, and it is 21, which is correct for this problem. Now, there's 2 more to look at here. I have 2 more we want to kind of take a quick look at, and that will be, let's see, extend that up there a little bit. These are going to involve addition and subtraction. Now, addition and subtraction are a little bit different. In this case, you don't look at the number of significant figures in each number. You look at the place where they end. For example, let's look at this one first, and let's say that this one ends in the 10th place. So this goes down to the tenths. This one ends in the ones place, and this one ends in the hundredths place. So each of them ends in a different place. When you're adding or subtracting, your answer cannot go past the one with the one furthest to the left. Whichever one has its last significant figure furthest to the left, whatever place that is, that's where your answer has to end. So this one goes down to the hundredths. We're not going to have hundredths in our answer because this one stops at the ones. This one goes down to tenths, but we can't have tenths in our answer because this one stops at our ones. So no matter what we add up here, we stop it at the ones place. So when we add and subtract those numbers, you get negative 150.72. Again, we want to stop at the ones place. Again, not worrying about the number of significant figures, and getting negative 151. So our answer would be negative 151. Yes, that has more significant figures than one of the numbers that went into it that only had 2. That doesn't matter when you're adding or subtracting. That only matters for multiplication or division. So in this case, your answer will be negative 151. You simply stop at the ones place, rounding off any decimal point that's there. Now our last example, we have again 3 numbers here. One has 1 significant figure, one has 2, and the other one has 1. And if we add those all together, we're going to get 585.003. Now, this one goes to the ones place. This one ends in the tens place. And this one goes down to the hundreds. And like the previous one, we can't end in ones because this one doesn't have a significant figure in the ones place. We can't end in the hundreds because both of these don't even go past the decimal point. So our answer has to stop at the tens place. If we round this to the tens, it's going to be 590. Now, you may look at this, it may look like you're making the numbers less precise. We knew it was 585.003. In reality, we did not know that because we only know that that number in the middle was 580. It only has 2 significant figures. That 0 is not significant. It wasn't exactly 580. It could have been 575. It could have been 584. Anything that you would round to 580. So as we can't know the last number any more accurately than we know the numbers, the answer we could not know any more accurately than the numbers that went into it. So this video has been to help you go through some examples of calculations and determining the number of significant figures in a number. And we will be using this throughout the course. So I'll be looking for answers that are in the correct number of significant figures, that are not overly rounded off, and that do not have trails of decimals that we know are not significant. As always, you can review this with me. You can come back and review the video. If you have questions, of course, come see me in office hours. And until next time, have a great day, everyone, and I will see you in class.